And there we go. Okay, what's your first question?
First question is whether I can use pH strips instead of cabbage. I can't think of a way to do that, but
You can, it'll be a little more difficult for you to do.
okay.
The way to do it is as follows. Do you know how? Well, let me ask you first, what kind of pH strip do you, or pH strips do you have?
I think they're just the universal kind. They're the high end, so they go from 14 to 1.
Okay, so they're wide, that's what we call wide range.
Yeah.
Okay, so you're supposed to take water and add a drop of sodium hydroxide to it, the cabbage juice, right?
Uh-huh.
And you're not supposed to have very much cabbage juice. It's supposed to be a very thin layer in your cup.
Okay.
And the reason you use a very thin layer is because if you put in a drop of the sodium hydroxide, it'll make the water basic.
Mm-hmm.
But if you use a pail of water and put that drop in, it won't make it as basic.
Okay.
Because concentration matters. It's kind of like putting, I don't know, honey on a biscuit. If you put one drop of honey on a biscuit, you might not notice it. But if you put like a big old layer of honey, or if you put a drop of honey on a tiny little biscuit, you might notice it very much so.
Okay.
So that's why in the videos, you may have seen that I recommend using a very small amount of liquid,
Mm-hmm.
just enough to be able to see the color. So you would do the same thing, only you wouldn't have the cabbage juice, you just use regular water.
Okay.
So if you put that drop in, what you have to do is swirl it. And with your pH strip, you don't want to ever dip it into your solution because it contaminates it. So what you'd want to do, I imagine you have like a ribbon, like you could roll it out like a piece of tape.
Yes. Mm-hmm.
Cut off little squares. So you want to have like, 20, 30 squares. And when you add one drop of sodium hydroxide to the liquid and stir it, stick a glass rod or maybe even your metal spatula
Mm-hmm.
in there and just get the tip wet and touch it to a piece of pH paper.
Okay.
And you'll be able to see the color.
Okay, that
Add
makes
another, yeah, add another drop in, swirl it, and touch it to a different piece of pH paper.
okay.
And by cutting it prior into little squares, you can separate them on a paper towel and they won't cross-contaminate one another.
Okay.
So you do that with the sodium hydroxide solution, you do that with the hydrochloric acid solution, and you do that with the sulfuric acid solution.
Okay.
Now, if the pH paper doesn't show much of a color change with each drop, then you might want to use even less water.
Got it.
Okay.
Okay.
And whatever amount of water you use for the sodium hydroxide, you want to use the same amount for the others. With the cabbage juice, you have more leeway there with how much you have in the containers than you do with pH paper. So you're going to have to kind of play with that.
Okay. I'm up to the challenge.
Yeah, so you can do that.
Okay. And next question is whether it's appropriate to record my observations in the data part of my lab, or should I put it somewhere else?
I consider observations to be data myself.
Okay, got it.
So data is just information.
Okay.
And observations is information.
Got it. And I was unsure if there was anything I should put in calculations.
In this lab, I don't believe there are any calculations.
Okay, that's how I felt too.
You don't really need to put anything there, but you do want to probably put some things in there like maybe an acid-base neutralization reaction, like some of the questions that are in the assignment.
Okay.
And you can put those anywhere you think it might fit. It might fit into the discussion very well.
Okay, gotcha. Or the balancing of the equations and what the products would be.
Yeah, I think that would actually fit into the discussion very well, because you would want to discuss why fewer drops of sulfuric acid should neutralize the sodium hydroxide than the more drops of hydrochloric acid.
Gotcha. Okay. And the the hydrochloric and the sulfuric, those were the only ones that I thought of to put in results of
Yeah.
when they, yeah, okay,
Those are the only two acids we're having you really work with.
okay, Okay.
You also might want to put in your results, the observation of what happened when you do the vinegar and the baking soda.
okay,
And you
gotcha.
might want to talk about that in your discussion about, well, I did see it foaming, and the foaming
Mhm.
must have been due to carbon dioxide.
Got
And, show a little balanced reaction there.
Got it. Okay.
And then, of course, with the redox one, you might want to put that in your discussion too.
Mhm.
Hopefully, you notice that bubbles appeared around the edge of the penny when you put it into the vinegar, but
Mhm.
it took a while. It takes
Got
a while because the acetic acid in vinegar is weak.
Weak. Gotcha.
You
Yeah.
put hydrochloric acid in there, it would have been bubbling like a boiling pot. Uh,
Okay.
but we want to be safe, so hopefully you notice some bubbles rising up, maybe appearing on the edge, like out of
Mhm.
nowhere. It's actually a reaction that's occurring on the surface of the zinc. And for me, I noticed after about 3 hours, and I'm not going to say it takes 3 hours. I'm just going to say I didn't look at it for 3 hours,
Mhm.
but there were little tiny bubbles rising off of the edge.
Got it.
If you look really closely.
Okay.
So you probably want to include that in your discussion too.
Okay.
But on the other hand, I could easily see you writing those up as results.
Mhm.
I noticed this, and this must be what's happening,
Got it.
something like that. So
Okay.
there's some variability there.
So it is appropriate in either fields, but it does need to be mentioned.
You should mention all those things. Yeah.
Got it. Okay. All right. I think that's all I needed. Yeah,
Okay, you checking out?
I am.
Okay, nice to see you.
Thanks. Mhm.
Okay, now let's see. We've got Greg. Are you there?
Yep.
Do you have any questions you'd like to ask, Greg?
No, me, I just like doing problems.
Okay. Well, I've done a lot of problems in the first two lectures. Or
I'd be
do you ever
happy. I'd
do
be
you ever
happy.
go back and watch those?
I haven't, but if that's what's available tonight, I'll be happy to.
Well,
No
no.
problem.
What I'm actually, I think it's going to be better for you if we look at these together than if you just watch a video.
Whatever you have time for, Tony, I'm all for it.
So the reason I'm asking you is because if you are going to go back and watch those, I don't want to do the same problems. But if you're not going to watch them,
It's
then I don't mind doing the same problems again.
it's an either or for me tonight. I could do either. If you're just going to do the same problems again, I'm happy looking at the video.
Yeah, but are you really going to get as much out of it, you think?
Nah, hey, I take a class because I want to hear you talk.
Well, here, I'll tell you what, we're going to go over some of these problems, and I want you to get a real good introduction into this chapter.
Okay.
And the chapter is called stoichiometry. And stoichiometry simply means relating amounts of different things in a reaction to the amounts of the other things in the reaction. And when I say amounts, it could mean, talking about if you start off with how many moles of this, how many moles of this are you going to make, and that kind of thing. Or it could be if you start off with grams of this, how many grams of this are you going to make? So stoichiometry deals with amounts. So let's take a look here. I'm trying to get this to focus. So you can see this is a pretty early problem in the back of the chapter. What mass of hydrochloric acid in grams is required to react with 0.750 grams of aluminum hydroxide? So naturally for this one, we're going to start with 0.750 grams of this aluminum hydroxide. And our eventual goal is to get grams of HCl. What mass in grams? So, the first thing to do is understand the problem. I want to go from grams here to grams here. Now, these reactions, when they're balanced, they have coefficients. And we know that if there's no coefficient written, it's 1. So here we have 1 aluminum hydroxide reacts with 3 hydrochloric acids to give you 1 aluminum chloride and 3 H2Os. So what do those coefficients mean when I say 1, 3, 1, and 3? Do they mean grams? And the answer is no. It means one of these reacts with 3 of these. And if we take a look, if it were grams, let's take a look at that 3 HCl and the 3 H2O. So basically you can see that 1 HCl gives you 1 H2O if it's a ratio of 3 to 3. Are you with me there?
Yeah.
1 HCl weighs 35 grams, actually 36.5 grams. So one of those weighs 36.5 grams. And if these ratios were correct, 3 times 36 is like 108. So that's 108 grams there. And if this were supposed to be also 108 grams, let's see if that works out. Each H2O weighs 18 grams. 3 times 18 is more like 57. So if you think about that, can 108 grams become 57? Does that make sense?
Correct.
So these numbers are not grams. All right. So a good way to think about the coefficients are as follows. 1 mole of aluminum hydroxide is equal to 3 moles of HCl. Now, once again, I'm not trying to convince you that these are the same thing. They're not. What I'm trying to convince you of is this. If you use a mole of aluminum hydroxide, you need 3 moles of HCl to react with it.
Right.
And likewise, if you react these together, you will get 1 mole of aluminum chloride, and you will get 3 moles of water. So that's what, oops, I didn't write 3 moles. Do you see that? Getting lazy. Okay, so that's what the coefficients mean. So the coefficients don't allow us to go from grams to grams directly. But here, do you see how we can go from moles of aluminum hydroxide to moles of HCl?
Yep.
So I'm just going to write that here because I can do that. And the reason I did this is because we should be able to go from grams of aluminum hydroxide to moles of aluminum hydroxide. What do we need to be able to do that? And the answer is the molar mass of
Aluminum hydroxide.
aluminum hydroxide. Excellent. And how do we go from moles of HCl to grams of HCl? We need the molar mass of
HCl. Yeah.
That's right. Now the molar mass of HCl is 36.46. The molar mass of aluminum hydroxide, I have to calculate very quickly here. We have 3 oxygens, so that's 48. We have 3 hydrogens, so that's 3.03. And we have 1 aluminum, which is 26.98. So this has a molar mass of 78.01. So for each of these arrows, if I write a little 1 here, a little 2 here, and a little 3 here, each arrow represents a conversion factor we want to use for this problem. So for arrow number 1, we want to use the molar mass of aluminum hydroxide. Do we want to put the 78.01 grams on the bottom or on the top?
Bottom. Moles on top, grams on bottom.
You got it. Now I sound like a commercial. You got it, Toyota. I don't know if you're old enough to know that commercial. Okay, now how about for number 2? What are we going to use there? And the answer is we're going to use the coefficients from the balanced reaction.
Okay.
So are we going to put the moles of aluminum hydroxide on top or the moles of HCl on the bottom, I mean, or moles of HCl on the bottom?
On the equation, you're going to want to cancel out the moles, so you put the moles on the bottom.
We're going to put moles of aluminum hydroxide on the bottom. And from the balanced reaction, there's 1, right?
Mhm.
How many moles of HCl?
3,
So we're going to put 3 moles of HCl.
3 to 1.
And then lastly, so that's number 2. For number 3, we're going to use the molar mass of HCl. I'm going to do 2 things here, and I hope I don't confuse you. The first thing I'm going to do is I'm going to put the 1 mole of HCl on the bottom and the 36.46 grams of HCl on top.
Okay.
Are you okay with that?
Yeah.
Now in the reaction, do you see it's actually 3 moles of HCl?
You already
So
took. Yeah. Okay.
students want to do this. They want to do this. You with me? But what is the mass of 3 moles of HCl? Well, it's 3 times 36.46, right?
Not what you want.
So if we do this, the 3's cancel and we have 36.46 over 1. So why even bother with the coefficient when you're using the molar mass? And the answer is don't.
Gotcha.
So don't do this. Just use the molar mass as is. So you might ask, well, where do we take into account the coefficients? Number 2. Number 2 is where we take into account the coefficients. Okay, so doing these conversions is as easy as 1, 2, 3. Molar mass, coefficients, molar mass. When we estimate this answer, I would gather that 36.46 goes into 78 about 2 times. 3 halves is 1.5. So 1.5 times 0.75 is probably around 1.1, right?
Yeah, 1.05. Yeah, 1.1.
Okay, so 1.05, excellent. And we get 3 significant figures because of this bad boy in front.
Correct.
So that is how we calculate the grams of HCl from this reaction. For this problem, if this were asked on a test, this is the work I would expect to see.
Okay.
Let me show you what would not get you very much credit. And when I say very much credit, I mean it gets you some credit, but not passing credit. So take a look at what we have here compared to what we have above. Can you see how what we have here is very deficient?
Absolutely.
First of all, you know, what kind of world is it where you trade 1 mole for 3 moles? I mean, I suppose if you're getting the 3 moles, you love that world. But if you're getting the 1 mole, you kind of like wondering, well, why, right? And here, what has a mole that weighs 78.01 grams? There's just no, and then here, ultimately, this equation says that your 0.750 grams is the same as 1.01 grams. So this is very deficient, and I would not give a person passing credit for that.
All right.
Okay. Now, what mass of water in grams is produced? So how would my map change if we're worried about water? So I'm going to scoot this down a little bit. So we want the mass of water, and we want to be able to see the equation. So we're going to start with 0.750 grams of aluminum hydroxide. What would I be getting first?
What do you mean as far as the equation?
Yep. Well, no, as far as the roadmap goes.
Oh, well, it would go to, what is it, 1 gram, 3 more, well, grams of H2O.
This is the map up here, right? I'm going to put parentheses around it. That's the map. So when we start with grams of aluminum hydroxide, what do we turn that into?
Moles.
Okay. And then what do we turn the moles of aluminum hydroxide into?
it would be 1 mole of aluminum hydroxide to 3 moles of H2O.
Okay, well, I'm gonna say we're gonna turn it into moles of H2O and then grams of H2O.
Okay,
So this is kind of the map. And then now we can fill in the arrows for the map, and which you're already doing. That's good. So what did you say? You said 1 mole of aluminum hydroxide on top, right?
yeah.
And 78.01 grams of aluminum hydroxide on the bottom. What are we going to do for the H2O and the aluminum hydroxide?
It's going to be 1 mole of aluminum hydroxide, and on top would be 3 moles H2O.
Right. And of course, the reason we chose it that way is so that
It goes
the
the same.
moles of aluminum hydroxide cancel. And then what are we going to do next?
I convert the grams of, you can give me a minute.
It's 18.02.
Yeah. H2O.
So we're going to do
1 mole,
18.
it would be 18 on top to 1 mole of H2O on the bottom.
Okay, let's estimate. How many times does 18 go into 78? About 4 times, right? Because that's like 20 and that's like 80.
Mhm.
So if that goes into that 4 times, we have 3/4, which is 3/4, right?
Okay.
What's 3/4 times 75? Well, it's got to be less than
25.
0.75. So maybe 0.60. Who knows?
Okay.
A little bit less, but not a whole lot less, right? So let's see what we get on our calculator.
0.5197, that would be 5.20.
So 5.520 grams of H2O. And that's what I would expect to see for your answer.
Okay.
Any questions there on how to calculate how much of one thing from how much of another?
Got it.
Now let me show you something else here. So you're supposed to ignore all of this here. And I'm going to write down that this is 0.750 grams. We just calculated that this is 1.05 grams. And we just calculated that this is a 0.520 grams. What's the one thing we're missing here?
Aluminum chloride.
Okay, can we calculate the grams of aluminum chloride that would be made?
Yes.
How would you do that?
Give me a second here. So it'd still take, it would be 1 mole of aluminum hydroxide, 3 moles of hydrochloric acid, 1 mole of aluminum chlorate, 3 moles of H2O. So I kind of got my ratios down. So it'd be 0.750 grams aluminum hydroxide times 1 mole over 78.01. And then we're doing moles to moles, so it's 1 to 1 on there.
Right.
1 mole of aluminum hydroxide. No, the aluminum hydroxide would be on the bottom. The aluminum chloride would be on top.
Good. And let's see, the molar mass of aluminum chloride.
You're going too fast.
Well, I'm actually figuring it out. I don't know it yet. So the molar mass of aluminum chloride.
And that would go, and the gram would be on top because you want that to cancel out to grams.
It'd be 133.33. Okay, so naturally you can see that for problems like this, you want to be pretty quick about figuring out molar masses.
Mhm.
So if this is 133.33, then we get
1.281, 1.282.
so 1.28 then.
Yeah, 1.28.
Okay, now I'm going to show you something that's tricky. Are you ready?
No, but go ahead.
um, shouldn't 0.750 and 1.05 equal whatever this number is plus 0.520?
No,
Why not?
could lose to gas, I don't know. Is it a ratio?
Well, what we're saying is that if you start with this is 1.80 grams, you should end up with 1.80 grams. Regardless of whether it's a gas or whatnot, you should end up with the same mass.
Because you can't create or just, okay, got you.
It's called the law of the conservation of mass or law of the conservation of matter, your choice.
Okay,
So let's see if that 1.8 minus 0.52, and we get 1.28. And is that what we calculated using? Oh, there it is. It's 1.28.
okay.
So what that's supposed to do for you, Greg, is give you confidence that you did this correctly. You got 1.28 two different ways.
Okay.
So you should be confident that this method works. Fair enough?
So I'll expect to see this on the test, right?
Well, stoichiometry, you're going to see it on almost every test from here on out.
Nice.
Okay. So let's take a look at another one here. I'm going to skip that one. And we're going to do this one here because this one includes a little extra. And the extra is you need to balance the reaction. So that's A, balance the reaction. So right now I'm just writing the reaction out.
Okay.
Okay, are we good on bariums?
Yep.
Are we good on chlorines?
We need 2 more. So need 2 in front of the silver.
Okay,
Okay.
so we're still good on bariums and we're still good on, now we're good on chlorines. Are we good on silvers?
We need 2 more silvers and 2 more nitrogen.
Well, how about we
nitrate.
do this instead? Do we have 2 nitrates here?
Yeah, that's it. Put the 2 in front of the
And
nitrate.
do we have 2 nitrates here?
And yes, no, you pointed at the wrong one. Yes, we do.
So we have
We have
1
6
nitrate in this formula, but since we have 2 formulas, we have 2 nitrates. Do you follow me there?
Okay,
Another way to say it is we have 2 silver nitrates. That's what the 2 means, right?
Yep.
So we do have 2 nitrates here and we
Yep.
have 2 there. So this is good.
Yep.
Now, what mass of silver nitrate in grams is required for a complete reaction with 0.156 grams of barium chloride? So we're going to start with our 0.156 grams of barium chloride. And we're going to turn that into moles of barium chloride. And we're going to turn that into, since they're asking about silver nitrate, moles of silver nitrate. And then into grams of silver nitrate. So that means we're going to need the molar mass of barium chloride.
Okay.
And just to save us some time, I've done this earlier today, and if I look in my papers, I can probably find it. Oh, I've gone too far, I think. I'm not having any luck finding it. Oh,
172.75 plus, there, give me a second here. That's 2 chlorides. So 137.3 plus 75. Oh,
well,
three.
actually, let's go to 2 places past the decimal. Because on your exams, the periodic table goes to 2 places beyond the decimal.
Shit. Okay, fine. Yes.
So barium is 137.33.
And chloride is 35.45 times 2.
Yes. So I get 208.23. Is that what you get?
Yeah, 2H. That goes on the bottom.
Okay, and silver over here is 107.87. And then you have 1 nitrogen which is 14.01. And 3 oxygens is 48. So here I get 169.88.
Okay.
Okay, so now you're going to tell me what numbers to put where?
Yeah, okay, so be 156 grams of barium chloride times 1 mole over 208.23 moles of barium chloride times 2 moles of silver chloride over 1 mole of,
Silver nitrate.
yeah, sorry, silver nitrate over 1 mole of barium chloride. And then I have to convert the silver nitrate into grams, and that was 1 mole on the bottom of silver nitrate over 169.88. So the 169.88 goes on top because we want grams at the end.
Right.
Okay, so
And if we estimate this number here, can you see that 170 over 208 is going to be a little less than 1? Let's call it 0.8. And 0.8 times 2 is like 1.6. So 0.156 times 1.5 puts us at like maybe 0.22 or something around there.
0.255,
Okay.
and that'd be grams
That's right.
of silver
Nitrate.
nitrate. Thanks.
Okay. Now I don't think we need to necessarily do this, but how would we get the mass of silver chloride? What things would change here? Would we still start with 0.156?
Yeah,
Would we still use 1 mole is 208.23 grams?
right. And then we use 2 moles of silver chloride over 1 mole of barium.
And then what would we use here?
The molar mass of the silver chloride.
Okay, so what I'd like you to do is I want you to go ahead and set up that problem. And while you're doing that, I will find out what the mass of silver chloride is, okay?
Yeah.
And I'll let you know.
Cool.
Okay, I've got it. You just let me know when you want it.
What's the molar mass, please?
143.32.
2 silver chloride. Okay, so 6 times 2 times. About 0.213, 214, 0.214
That sounds right.
grams
Of silver chloride.
silver chloride.
Okay, so you got it.
Okay, yeah, cool, good, thanks.
This is something you're definitely going to need for the exam, but there are other things that we also need to know for the exam. That's just the beginning. So let's take a look at another problem here. This one is a little different. So this one is iron ore is converted to iron metal in a reaction with carbon. And here we have a balanced reaction. You can see we have 4 irons on the left, 4 on the right, 6 oxygens on the left, 6 on the right, 3 carbons on the left, and 3 on the right. So this is balanced. So how do we do a problem like this where we want to go from moles of iron 3 oxide to moles of carbon? When they say amount here, in this case, since they're starting with moles, they want you to end up with moles, okay?
Okay,
So we're going to go from 6.2 moles of iron 3 oxide to question mark moles of carbon. Can we do that directly with a balanced reaction?
yeah, why can't you? Well,
It's no why can't you, it's of course.
yeah,
You're
we
right.
can. Yeah,
Of course you can.
because you already know the ratio.
Yeah. And this one, it seems absurdly simple compared to what we just did, doesn't it? But it almost seems too simple, like we're being tricked.
Uh-huh.
But indeed, we're not. This problem is just to get you to understand that the balanced reaction allows you to go from moles to moles and not directly from grams to grams. So that's what we would get. How would this change for iron?
It would be 4 moles of iron over 2 moles of iron, the iron ore.
That's right. Now, this one is tricky. What do you get for the answer once you write it out?
Uh, 12.6 moles of Fe.
Well, this should be 6.2, so that would be 12.4, wouldn't it?
Yeah, well, yeah, that's what I get for doing it in my head.
Okay.
Oh, yeah.
And the answer would be 12 moles of iron. Why would it be 12 instead of 12.4?
Just round.
How many significant figures in 6.2?
1.
Oh, no, there's 2.
Oh, okay.
How many in 12?
0. 1.
2.
Oh, okay.
All non-zero digits are significant. So 1, 2, 1, 2.
Gotcha.
How many significant figures are in these coefficients when we make sure that there are exactly the same number of atoms on each side?
I don't understand the question.
So how many significant figures in the 2 here, the 3 here, the 4 here, and the 3 here?
All 1.
Nope. Well, let me ask you this. Do we think this 2 could be 2.1 or 2.2?
In this equation?
Yeah.
No.
No, it's exactly 2, isn't it?
Right. It's 2, 3, 4, and 3. Yeah.
Yeah. So that means there are exactly 4 iron atoms here because that's exactly 2, and that's exactly 2.
Oh, okay.
So how many significant figures in something that we know for darn sure is 2 and only 2?
I'm still a little confused, but 2.
Well, if I write that 2 out, what number would I write after it?
2.0,
How about after that 0?
0,
How about after that 0?
infinity. It's a
It would go to infinity, wouldn't it?
correct.
Now, according to our rules, would these zeros count if we have the decimal and they're trailing?
Yes.
Yes.
Well,
So how many
yeah.
significant figures would this guy have?
no, 4.
Infinity,
Well,
because it goes forever, right?
yeah.
So this is one of those things where if you have a number that's counted, like the number of atoms here, that number has an infinite number of significant figures. The other types of numbers that have an infinite number of significant figures are those that are defined, like 12 inches is 1 foot. No ifs, ands, or buts. It's not like 12-ish, it's 12.
Okay.
How many significant figures in 12 for 12 inches equals 1 foot? Well, infinity.
Yeah.
Okay, so here we've got 2 zig figs because that's not counted.
Mhm.
And we got 2 and 4, those are infinite, so we get 2 zig figs.
Okay.
Just like up here, we got 2 zig figs to begin with, we end up with 2 zig figs.
Gotcha.
So this is interesting, and this is why this is tricky, is you really have to keep track of significant figures and remember those rules.
Gotcha.
Okay. So we're done with that one. This next one is more interesting. This is called a combustion reaction with a hydrocarbon. Do you see the formula for ethane?
C2H6.
Right. This is called a hydrocarbon because of the hydrogen and the carbon, hydrocarbon. And they probably called it hydrocarbon instead of the other way around because it sounds better. Carbohydrogen just doesn't have the same ring to it. So hydrocarbon. It burns in oxygen. Whenever you burn a hydrocarbon in oxygen, you get 2 things if it burns to completion. Those 2 things are carbon dioxide gas and H2O liquid. So you want to memorize that. So for A, they want us to have a balanced reaction. So we're going to put C2H6. You don't know this, but I'm going to tell you that this is a gas at room temp. You react it with oxygen, which you already know is a gas at room temp. And you get carbon dioxide, which is a gas at room temp. And you get H2O, which is a liquid at room temp.
Okay.
So I want you to memorize that. When you burn a hydrocarbon in oxygen, you get CO2 and H2O. Okay. When you balance these reactions, you want to balance starting with carbon, and then hydrogen, and then oxygen. Another way to think about it is balance it in alphabetical order. So carbon is 2, carbon 1. I'm going to put a 2 here. Sound good?
Yep.
6 hydrogens here,
3
2 here, so I'm going to put a 3 there. 2 oxygens here, 4 here,
6.
but also 3 over here.
So we need 3 more over here.
So we have 7 oxygens here, and here we only have 2. What can we do to get 7 oxygens over here? And here's the trick. I'm going to use a half, 7 halves oxygens. So what's 7 halves times 2?
7.
Yeah.
Oh, so you
So-
make 7 and 14. Got you.
Yeah, so that's, yeah, you can see where we're going with this. We have 7 oxygens now, but we don't like these types of coefficients. So what can we do to keep the ratios the same and get rid of the half?
multiply both sides by 2.
Right. So we're going to have 2 C2H6s. We'll have 7 O2s. We'll have 4 CO2s. And then we'll have 6 H2Os. And, let's double check and make sure we did okay. How many carbons on the left?
On the left, 4,
How many on the right?
4,
How many hydrogens on the left?
12,
And on the right?
12,
How many oxygens on the left?
14.
Now there's 2 places on the right. How many in the first place?
It's 8 and 6.
And 8 plus 6 are?
14.
14. No, not 14, but 14 alone, okay?
Thanks, I appreciate that.
And we have 14 on the left, so it works out.
Gotcha.
So this is where the half trick really is kind of nice. Okay, so that's A. B. What mass of O2 in grams is required for complete combustion of 13.6 grams of ethane? I'm going to put the molar masses of each of these underneath them. So 18.02 for H2O, 44.01 for CO2, 32.00 for O2, and for ethane, it's going to be 30.08. So those are the molar masses. I'll put a little MM next to each of these so that you know it's a molar mass, okay?
Gotcha.
And that'll save you the time of having to calculate those. And we're going to start with 13.6 grams of C2H6. And I want you to go ahead and figure it out. And when you're ready, just let me know and we'll do it together just to make sure you got it right.
And I'm solving for mass.
Mass of O2.
Okay. So it's 13.6 or no more over 13.6 grams C2 times 2 mass of O2 times. So it'd be 13.6, was it ethane times 1 mole of ethane over, wait a minute, what was the third, that was 30.08. So it'd be 13.6 grams of ethane times 1 mole of ethane over 30.08 moles of ethane.
Grams.
Grams, yeah, grams of ethane times 4 moles of O2 over 2 moles
Where do you
times,
get 4 moles of O2?
oh, 7 moles.
Okay.
7 moles, sorry, my bad. 7 moles of O2 over 2 moles of the C2H6 times 18.02 grams of O2 over 1 mole of O2.
I think you're hurrying yourself too much. 18.02 is for water.
Honestly,
So we're going to use 32 for O2.
because there's 2 moles of water. Gotcha.
Well, no, not because it's 2 moles of water.
I mean, 2 moles of, it's, okay,
Because there's 2 moles of oxygen.
right, 2
They're
moles.
each 16.
Gotcha.
And if we work with this, can you see how 32 divided by 30 is about 1?
Mm-hmm.
2 goes into 7 3.5 times. So 3 times this is roughly 40. 4 times this is roughly 55. So the answer is somewhere between 40 and 55, right?
Uh,
And I get 50.6.
You're doing better than I did. Okay.
So this is the answer for A. Here's the answer for B. For C, they want to know, what is the total mass of products that you expect?
Well,
Total-
if I have the two on, I have the C2H6 and I have the O2, I can add those two together and determine it'd be about the same.
Not about,
It would be the
the
same. Yeah,
same,
it would be the same, yeah.
the same. So 13.6 grams plus 50.6 grams is equal to 64.2 grams total.
So that,
Yeah, so we can say that we're going to get that many grams total, but it doesn't tell us how much of each one.
gotcha. Okay,
Any questions on that one?
nope.
Okay, so we're going to get progressively harder, as it were. Now, this one is called a limiting reactant problem. So, you know, a great question is, well, what's a limiting reactant problem? Well, before we get into too much detail with this one, here's the idea behind limiting reactant. Okay, so I'm going to teach you how to draw a bicycle. First, you draw a triangle. It doesn't matter whether you draw the base at the bottom or the tip at the bottom. It doesn't matter. Once you draw one of these triangles, draw another one next to it like that. And can you see how if I put a little J there, I've got a bicycle fork?
Sure.
And then there's my handlebar. You can make it go the other way if you like a road bike and you want drop handlebars. And there's my seat. Now you're going to be really impressed by my wheels. There's a wheel. How many of these do I need for my one bicycle frame?
2.
So I'm going to put a 2 here for a balanced reaction. Now we're going to draw the bicycle. So again, you start with the triangle, draw another triangle, and make sure you put the fork in the right place. And when you put the wheels on, I'm going to put little dots here. That's going to be the center of each wheel. And there's your bicycle. So can you see how the ratio is 1 to 2 to 1? One frame and 2 wheels get you one bike. Are you good on that?
Yep.
Okay, now I have seen this lecture delivered in Davis. And I was really surprised that they used this analogy because I've been doing this for years and I thought I was the only one stupid enough to do it. At Davis, here's how they teach it. Guess what that is? That's your bicycle frame. What's that?
That's the tire.
That's a wheel. And there's your bicycle. So this is College of the Redwoods. This is UC Davis. You can see how you're getting a much better education here at CR. Okay. Now, when I say I've seen,
was that teacher Huber that I just heard?
yeah, absolutely. But I'm not lying when I say I've seen this lecture at UC Davis because I sent my daughter there. She was taking chemistry and having a heck of a time. So I used to go down and help her. And one time I caught a lecture and they drew this. And I would lean over my daughter and I said, oh, we draw a much better bicycle at CR. Okay, now remember, we're talking about the idea of limiting reaction, okay? So I'm going to draw this kind of hurriedly. Now, if I had 2 frames and excess wheels, now what do I mean by excess wheels? I mean
You'd have
as
5,
many as I need. How many bikes would we make?
2.
2. Now, what if we had excess frames, but only 10 wheels? How many bikes could we make?
5.
5. Okay, so here, the wheels are in excess, the frames are in excess. It's really easy to see because I said as much. So this is case 1, this is case 2. Now, what if we run into a real situation where maybe you have 2 of these and 10 of these? How many bikes are you going to make?
2.
2, because you run out of frames, right? So in this case, the frames are said to be limiting because they limit how many bikes you can make. And the wheels are in excess because you're going to have leftovers. In fact, we'll have 6 leftovers. Wouldn't you agree?
Yep.
Okay, so limiting and excess. So how do we discover which one is going to be limiting and which one's going to be in excess? There are 2 ways to do it. One way to discover which is limiting is to do this. 2 frames times 1 bike per 1 frame gives me 2 bikes. So I'm doing this case here first. 2 frames times 1 bike per 1 frame to get 2 bikes. Are you with me?
Gotcha.
Now, 10 wheels times 2 wheels per 1 bike gives me, oh, I did that backwards. Do you see that?
Yeah, 20 wheels now.
So it's 10 wheels times 1 bike over 2 wheels. So how many bikes does that give me?
5.
5 bikes. So the smaller number tells you that the frames are limiting, and the bigger number tells you that the wheels are in excess. So the smaller number tells you that what you began with is limiting. The bigger number tells you which one is in excess. Just like we discovered up here, you know, between the 2 and the 5, we got 2 here. The smaller number tells you how many you're going to get. Are you with me?
Yep.
Let me show you another way to figure out what is limiting. And this is a really good way also. So we have 2 frames and we have 10 wheels. And we want to find out what's limiting. What we do is we start off with our 2 frames and we multiply by 2 wheels per 1 frame. Where do I get that ratio from?
The structure of a bike.
Also, I would say the balanced reaction,
Oh, okay.
right? I'm drawing my reaction again.
Gotcha.
So remember, the analogy is such that this is a balanced reaction above. So this says that we get 4 wheels. So what does the 4 wheels mean? This means
That my wheels are limiting.
we need 4 wheels for 2 frames. That's what that means. Now, we have 10 wheels, and we only need 4. So what does that mean about our wheels if we need 4, but we have 10?
We got more wheels than we need.
Yeah, so we have 10 wheels, use 4, 6 left over. So when you have leftovers, that's excess. And if we know the wheels are in excess, what does that mean about the frames?
They're limited.
They're limiting. Now, what if we didn't know that the frames were limiting and we started with wheels instead? So let's take a look at 10 wheels. 1 frame per 2 wheels, right? So this says 5 frames. So what does this mean? This means that for 10 wheels, you need 5 frames.
Right.
So it means you need 5 frames to use all 10 wheels. But here we only have 2 frames. Only 2 frames means you do not need all 10 wheels. So what does that tell you about your wheels if you don't need all 10?
Excess.
They're in excess. So wheels are in excess and the frames are
Limited.
limiting. Now, the reason we went through this is just to show you that it doesn't matter what you start with, you're going to get the same results. In both cases, the wheels are in excess and the frames are limiting. Are you with me there?
Yep.
Now, if we had to calculate how many bikes we would make, we'd start with the 2 frames and multiply by 1 bike per 1 frame and get 2 bikes. Okay, so 2 ways to figure out what's limiting. One way is to figure out how much you need of the other thing and then compare. And then once you find out what's in excess and what's limiting, figure out how much you're going to make. Or we could do it that other way where you figure out how much you're going to make of each and you're going to go with the lesser amount. So let's take a look at this problem here and let's do this both ways to see if we get the same result. So we have ammonia gas can be prepared by the reaction of a metal oxide with ammonium chloride. What type of reaction would you call this? Would you call it a redox, a precipitation, an acid base, or a gas forming?
Gas forming?
Gas forming because of the ammonia.
Yeah.
Okay. So if 112 grams of calcium oxide and 224 grams of ammonium chloride are mixed, what is the limiting reactant and what mass of NH4 can be produced? So let's get some molar masses first. I'm going to write calcium oxide. We're not going to worry about the state. We do want the coefficients in there. I'm going to put some molar masses that I happen to know off the top of my head. This is 18.02. This is 17.04. This is this one I have to do as 18.05 plus 35.45. So this one is 53.50. Calcium is 40.08. So here, this one is This one is 110.98, and this one is 56.08. So these are the molar masses right here.
Okay.
Okay.
Start off with-
So let's do it the way where we take 112 grams and find out how much product we're going to make. Now, we could do this with ammonia, we could do this with water, or we could do this with calcium chloride. It doesn't matter which one we work with.
Right.
Considering that they want to know what mass of ammonia is going to be produced, I would suggest we calculate the amount of ammonia we'll make. How's that sound?
Sounds good.
Okay, so we're going to start with 112 grams of calcium oxide times 1 mole of calcium oxide per,
56.08 grams
yes,
times 2 moles of ammonia
yep,
over 1 mole CaCO, calcium oxide,
and then times,
times 17.04 grams. I'm sorry, that's wrong.
no, that's right, 17.04 grams of ammonia per 1 mole of ammonia.
1 more, yeah, one. Would I? Okay, no problem. Already got the 2 moles in there.
Yeah, you want to put a 2 there, right?
Yeah, but I already took care of it right before there.
Yeah, and if we
Yeah.
did put a 2 here, wouldn't we have to multiply 17 by 2?
Yeah,
So why bother?
right. Yeah, I sorry, I just happened to notice.
Well, you just got introduced to the topic today. Don't expect you to master it yet. But you're doing a good job.
It's,
I mean, you are thinking through, your decision making, and that's good. So my calculator gives me 68.1 grams. Do I think that's correct?
68. Yes.
I think
60.
it must be close.
Oh, yeah.
17 goes into 56 about 3 times. 3 goes into 112 about 36 times or 38 times. And then 38 times 2 is like 74, and I get 68, so I'm good.
Okay.
68.1 grams of ammonia. Now let's do this with the 224 grams of NH4Cl.
Okay. 224. And what are we calculating for? We're doing for the same material again?
Absolutely, because we want to know how much NH3 can be produced.
Okay, so it'd be 224 grams of NH4Cl times 1 mole over 53.50 grams of NHCl times 2 over 2 moles of NH3 over 2 moles NH4Cl times 17.04 grams NH3 over 1 mole NH3.
Okay, when we estimate this, 17 goes into 53 about 3 times. 2 divided by 2 is 1. 3 goes into 224 7.75 times. So I think the answer here is going to be close to 75.
71.3.
So you get 71.3 grams of NH3.
Mhm.
So if in one case you can make 68.1 grams, and in the other case you can make 71.3, how much will we really make?
Well, if we only have 112 grams, we're only gonna make 68.07.
Right, because once we make 68.1 grams,
That's
we
it,
run out of the calcium oxide, don't we?
yes.
So that means that this is limiting because we get the smaller amount, and this one is in excess.
Gotcha.
So this is the answer to A, or not to A, this is the answer to all of it. We got the limiting, we got the excess, and we got, this is how much we make. Are you with me?
Yep.
Now let's do it the other way. So the other way is going to be this. We're going to take our 112 grams of calcium oxide, and we're going to calculate the amount of ammonium chloride we need. So do you see what I've done here?
Okay, again, you're getting moles of calcium chloride.
And now we're going to get moles of ammonium chloride. So do you know where I get this from, this ratio?
1,
2 to 1?
yeah, from the equation.
Great. And then
Yeah.
finally, we have 17, actually 58. No, where is it? 53.50. So here we're calculating the amount of ammonium chloride we need for our 112 grams. And you can see that when you have 56 and 53, this is really close to 1, right? And so 2 times 112 is 224, but the answer should be a little less than 224. Let's see what we get. I get 214. How about you?
I'm still writing.
Okay.
So what we're saying is if I have 112 grams of calcium carbonate, I need 214 grams of ammonia chloride,
Ammonium.
ammonium chloride.
That's right.
So again, it's showing that, well, it's telling you how much you need of each.
Right.
Okay, yeah,
So what does that tell us when we have 224 grams of ammonium chloride?
we got plenty.
We've got extra.
Yeah, we got more than enough. It's not the limiting factor.
So we have excess ammonium chloride because we've got 224, right?
Okay, yes, correct.
Excess, I'm going to put because you need 214, you have 224.
224, yeah,
Okay, so what does that mean about the calcium oxide
that's the limiting factor.
limiting?
Limiting.
Now, if we had done the problem this way, does that tell us how much ammonia we have?
We can calculate it, but no.
No, it doesn't. So we have to calculate it. Now, if we know that calcium oxide is limiting and ammonium chloride is in excess, what do we want to start with to calculate the amount of
Calcium.
ammonia?
The calcium chloride.
Exactly.
So 112 grams calcium chloride.
And you can
do
see that
full
this
conversion.
is going to be exactly the same as this up here, right?
Right, right.
So we get 68.1 grams of ammonia. And that would be our yield, if you will. So if you take a look at the way we did the two problems, do you see that one problem, one way of doing it versus another doesn't really save you any work?
Yeah, got you.
So which way are you going to do it? And the answer is whichever way you feel most comfortable with. Okay?
Okay.
All right. Let's see. I think that's good enough. That's about as far as we got this morning.
Nice.
I will show you this one here. Do you see how this is a limiting reactant problem also?
Okay.
Now this one's a little different. They do ask what's the theoretical yield. So that's pretty much what we did before. But here, what mass of excess reactant remains when the reaction is complete? So with that little extra question, I want you to take a look here. Which of these ways is going to tell you how much excess ammonium chloride you're going to have?
I personally, I like the way we're doing it at top, but the one on the bottom will give us the yield pretty quick.
Well, and the one on the bottom says you're going to use 214 grams, but you have 224, which means you have 10 grams excess, right?
Correct.
Where do we get the 10 grams excess above?
But we didn't. You're just saying you go with what you're more comfortable with earlier, and I'm more
Yes.
comfortable with what's above.
So
So-
if you did do what was above, you would then have to do a couple of more calculations. One would be take that 112
Right.
and calculate this to find out how much you would use, right?
Right.
And then once you find out how much you would use, subtract it from how much you have to get the excess.
Okay.
So this one would require a little extra step, but for me, I like the above one better, but you know, it doesn't matter. Apples and oranges, they're both fruits and they're both healthy for you.
Hmm.
Fair enough?
Yep.
Unless of course you have one of those sensitive stomachs where you can't handle acids from citrus, then apples are definitely better for you. And I got to tell you this, I've never met an apple pie I didn't like, but I've never met an orange pie.
That's pretty bad.
Have you ever had an orange pie?
No.
No. Kind of makes you wonder though, why not? They make orange tarts, right?
I have had apple tarts. I haven't had orange tarts. I've had
Haven't
cherry.
you ever had like a little tart with little orange slices in it?
No, I've had lemon tarts, but I haven't had orange.
Well, if they can do that with lemon, they should be able to do that with orange, right?
Well, yeah, you'd assume, yeah. Yeah,
But
you
they
asked
make
me.
some, they make some
you're asking-
pastries with orange slices.
You asked a question. I told you what I tried.
Well, listen, buddy, I think you need to invent the orange pie and sell it.
I'll remember that after class.
You just think about that. You could be the man who invented the orange pie, made it popular in the United States.
Well, I would know that I'd have at least one customer, right?
Yes.
Yes, yeah.
And-
The only person who would be interested in trying it.
Maybe not. I mean, it could be interesting, Greg. I'm just saying.
You got
Here's the deal, though. If you do become very radical and invent the orange pie and sell it, and you become a millionaire, I just want 10% of the net, not the gross, just 10% of the net for the idea.
Have you always been greedy like this?
10% is not greedy.
You know,
Most people charge a finder's fee of like 20%.
you know, how about this? I'll remember you as the chemistry teacher who told me how to mix it all together. I'll name it after you.
Okay, so when you go on the Today Show, you just tell people, yeah, I had this chemistry professor that was talking about apple pies and orange pies, and he was a little crazy.
Well, granted, I'll agree with that. Hey, I do appreciate you taking care of class tonight. Thank you.
Yeah, no worries. I'll be honest with you, Greg. You know how many people called in today?
Two.
You have doubled the number that actually called in. It's only one.
Well, if you don't have your recorder on, I'll say I'll be happy getting a personal class every night.
Well, I did record this and I'm going to post it.
Okay, well, then with saying that, I'm going to wish you a good evening.
All right. You have a good one, Greg. Bye-bye.